In this video, we are going to start our series on Fourier transforms. This is the overview slide for this video. We'll go over each topic very briefly before we cover each topic in more detail and with more examples. The first thing we will do is review some key points from the Fourier series, which was covered in our previous videos. Next, we will start looking at the Fourier transform. Unlike in Fourier series, we want to be able to use our Fourier transforms now in functions that are not periodic. And the way we do that is we look at our formulas for Fourier series and we consider T0 the period approaching infinity. And then we are able to get this equation here. We can represent our non-periodic function f of t as 1 over 2 pi the integral from negative infinity to infinity I e to the omega t times our Fourier transform. And our Fourier transform is 1 over square root of 2 pi, integral from negative infinity to infinity, f of t, or f of tau, e to the minus I omega tau. Often this formula is broken up into two parts. First, the Fourier transform is taken out, so it is f of omega equals 1 over square root of 2 pi, integral from negative infinity to infinity, e to the minus I omega t f of t. And then f of t, our final formula for our function f of t in terms of sines and cosines, is equal to 1 over square root of 2 pi, integral negative infinity to infinity, e to the I omega t, and then we plug in our Fourier transform here. A couple of notes about this Fourier transform. You see that we start with a function of t, of time, and we end up with the function of omega, of frequency. For this reason, it is considered a transform because we're transforming a function of time into a function of frequency, or said another way, this is, I guess, the way a lot of engineers will say it, is they say we are transforming from the time domain into the frequency domain. So this representation of f of t breaks down into two steps. First, we find the Fourier transform using this first formula, and then we find f of t using this second formula. There are a couple of other notations sometimes that is used, that f of omega is equal to this fancy f Fourier transform of f of t, or f of t is the inverse Fourier transform of f omega, where this fancy f is equal to 1 over square root of 2 pi, negative infinity, infinity, e to the minus I omega t. And here's our formula for the inverse of our fancy f, which is 1 over square root of 2 pi, integral from negative infinity, infinity, e to the I omega t. That covers our overview, so let's go back and take another look at our Fourier series. I've moved my formula for Fourier series and their coefficients right over here. Just kind of moved it down so I can work with it. And the goal of the Fourier series is to take a periodic function and represent it in terms of sines and cosines. That's this e to the I omega nt. And we can see that explicitly because remember, by Euler's formula, e to the I omega nt is equal to cosine omega nt plus I sine of omega nt. Remember, Euler's formula is what allowed us to convert from this exponential form to our sine and cosine, or our trigonometric form. The next thing to note about this formula is that it is the sum of n frequencies, this omega n. There's, n to the negative infinity to infinity, different terms of this frequency. So it's a sum of an infinite number of frequencies, and this Cn is like the weight. That gives us, this coefficient gives us a weighted sum of these sines and cosine functions of different frequencies. If you've had linear algebra, another way of saying this is this sum here is a linear combination of sines and cosines of different frequencies. Turning next to our formula for coefficients, we see we have an integral of f of t with our sines and cosines, e to the I omega nt. And Again, appealing to linear algebra, an inner product of two functions f and g is equal to the integral of f and g over dx. And when we say this integral is an inner product, what we are saying is this integral obeys certain properties. Once it obeys certain properties, we classify it as an inner product. And one of the consequences of being an inner product is if our two functions are orthogonal, that means their inner product is equal to 0. So whatever intuition you have for orthogonal or angles that are 90 degrees to each other, where their dot product is equal to 0, that's what carries over with this inner product now and this integral. Now, since sine and cosine are orthogonal, and that's something we had discussed in a previous video when we were talking about Fourier series, and we also saw that sines of different frequencies and cosines of different frequencies are orthogonal. This integral for Cn picks out the frequency Wn. In other words, in this formula for Cn, when we integrate the function f of t with the sines and cosines, and remember this is an inner product, this e to the I omega n that represents sines and cosines of frequency n. They'll all go to 0 except for when the frequency Wn equals the part of f of t that is at that frequency. So again, Cn will pick out the frequencies Wn in the function f of t. And that is how we get our weight for our function f of t equals these sum of sines and cosines. I think that's enough review of the Fourier series. Most of these things I have at least alluded to in our previous video, and a couple of the things I may not have spelled out as explicitly as I have here. So I think this was a good way of kind of wrapping all this stuff up for Fourier series. We are now ready to talk about Fourier transforms. I will be spending most of my time talking about how to interpret or kind of making some of the formulas more intuitive and then doing an example. Before I do that though, I will spend a little bit of time discussing the approach to getting these formulas. I will not actually derive the formula, but I'll talk a little bit about how we come to them. The way we approach Fourier transforms is to look at Fourier series as our period t0 approaches infinity. This is our formula again for our Fourier series. The one thing we did do here to simplify our discussions is make the limits of integration shifted over so they're symmetric about t equals 0. Also, we want to note that the Cn coefficients are the complex amplitudes over here of the discrete Fourier components which make up f of t. As our period t0 grows larger to infinity, the Fourier series still generates a spectrum, but the discrete frequency omega n, which is equal to 2 pi n over t0, become packed together. So here we have our original Fourier series with period of t0, and it's symmetric about our t equals 0 axis. As we stretch out our period, our function stays the same, but now we're going to stretch it out over both sides until we have this function that is no longer periodic. And then just a note, our omega n, since t0 is becoming larger, this omega n becomes smaller and more packed together. Then functions where t0 approaches infinity can be analyzed with the Fourier transform, which can be derived carefully considering the Fourier series equations over here in the limit as t0 approaches infinity. And the equation we get is f of t will equal to 1 over square root of 2 pi, integral from negative infinity to infinity, e to the I omega t times this inner function, 1 over square root of 2 pi, integral from negative infinity to infinity, f of tau, e to the minus I omega tau. This inner function is considered our Fourier transform, and this outer function f of t is considered the thing we plug in our Fourier transform to. So we can think of analyzing a non-periodic function f of t over here using two steps. The first step is to find the Fourier transform, and the second step then is to plug the Fourier transform into this formula here, f of t. I want to make a few notes about Fourier transform that hopefully will make it more intuitive or kind of explain what's going on. So here I have the full formula for f of t, and then that has the inner part, which is the Fourier transform, and then I broke this out to the Fourier transform part of the equation and the f of t part of the equation. And the first thing to say about these two equations is they're practically identical. They both have the 1 over square root of 2 pi. They both integrate from negative infinity to infinity. They both have the e to the I omega t. The difference is the Fourier has a negative I omega t. This f of t has a positive e to the positive I omega t. And then they both have either little f of t here or capital F of w. So the difference is this is dt with respect to t with this function f of little t, whereas this formula is d omega with the function being multiplied is capital F of omega. Now let's focus a minute on this Fourier transform. And as I had mentioned before, it takes this function of time, and in the end, you get this function of frequency. And that way, it is considered not just an integration, but it is actually a transform, and that you're transforming from a space or the time domain into the frequency domain. And the way to see this is that when you do this integral with respect to t, you are in effect integrating out the t. And what I mean by that is if you remember in vector calculus, when you would do double integrals, so you would integrate with respect to x first, and then you would integrate with respect to y. So first, just this part here, this green part of the integral, when I integrate with respect to x, I pretend like y is just some constant, if you recall. So I integrate this. If I'm integrating with respect to x, this x squared becomes 1/3 x cubed, and this y, if y is just a constant, integrating with respect to x, this becomes xy. Then I plug in my limits of integration, 0 and 1, and I'm finally left with 1/3 y plus y, and then I have my integral from 0 to 1 dy. And what you can see is what I've done when I integrate with respect to x is I've gotten rid of my x variable. In other words, I've integrated out the x. In the same way is in this integral here, when you integrate with respect to t, you're integrating out the time variable. You're integrating out t, and what you're left with is this omega. So then you're going to be left with the function f of omega. So you're going from a time domain, or where your domain, your x-axis is time, to now you have a function where your x-axis is omega, your frequency domain. And I went ahead and wrote that out. So f of w, it transforms a function of time into a function of frequency. Instead of this little f of t, we now have capital F of omega. So it transforms from the time domain to the frequency domain. Of course, the next thing to consider is we have this second step, this f of t over here, which is equal to 1 over square root of 2 pi, negative infinity to infinity, d omega, e to the I t, our Fourier transform. So it's like, well, what the heck? We just went to the frequency domain. Why are we coming back to the time domain? It's like we just undid all the work we have just done. But the thing is we really haven't, because at this point, this f of t is going to be different from our original f of t, and that this f of t is going to be written in terms of sines and cosines. So we'll do an example so you can see that that is the case. We're not just going to end back with our original f of t. We are going to end up with a different function of time that is written in terms of sines and cosines, or e to the I omega t, which is really the same thing. Our first example is a square wave. F of t is equal to 3 when t is between -2 and 2. 0 when the absolute value of t is greater than 2. And this is our drawing of our square wave. And we want to find our f of t here. The first step is to find the Fourier transform, and I moved my formula here. And plugging in, we have 1 over square root of 2 pi, then our integral from negative infinity to infinity, well, we're 0 everywhere except between negative 2 and 2. So we'll plug in negative 2 and 2. I mean, if you really want, you can go from negative infinity to negative 2, but then you're going to have the integral of 0. So it's going to go to 0. And you can also do the integral from 2 to infinity, but then you're going to have to plug in 0 for your function, so the integral will go to 0. So we're just going to stick with negative 2 to 2, and then we have our function. Where is my formula? F of t, which is equal to 3, and then e to the negative I omega t, which I have written here. I've pulled out my 3 to the outside, and now I'm left with the integral from negative 2 to 2, e to the minus I omega t. My I and my omega now, because I'm integrating with respect to t, I forgot to put my dt here, but pretend I did. Since I'm integrating with respect to t, my minus I omega is considered a constant, so I'm going to pull that out, minus 1 over I omega e to the I omega t, evaluated at 2 and negative 2. I plug in my limits of integration, I plug in 2, so I have e to the minus t is equal to 2 I omega minus, plugging in my other limit of integration, that will give me minus 2 for t, so I get e to the 2 I omega. So what did I do next? Oh, I remember. I want to convert this now to my sines and cosines. And I'm going to use this formula that I've gotten from the Euler formula, and we derived this when we were talking about Taylor series. So my sine in terms of e to the I theta looks like this. So here I need my positive exponent, this over here, to be positive. So I take this minus 1 here and I multiply it inside. So then I have e to the 2I omega minus e to the minus 2I omega, which almost looks like this. And again, I'm thinking of theta in this case as being 2 omega. I just need to introduce a 2 in the denominator, so I'll have to put a 2 in the numerator, which I have done here. And then finally, I can multiply this stuff out, and I get my 6 on top, my square root of 2I omega, and then I have my 1 over 2I e to the 2I omega minus e to the minus 2I omega, using my sine formula, so I have sine of 2 omega. And again, this is my Fourier transform. It takes a formula in the time domain. This is my f of t, right? It was a formula that took time as its input, and now I have a new formula, f of omega, which takes omega, a frequency, as its input. That again was step 1, to find the Fourier transform. Now again, to represent f of t in terms of sines and cosines, we need to do step 2, which is to plug in our Fourier transform into this formula, which I've copied over here, for f of t. So I have f of t equals 1 over square root of 2 pi, integral from negative to infinity d omega, e to the I omega t, and then my f of w I have copied over here from my previous slide, from our previous work, is 6 over square root of 2 pi omega sine of 2 omega. I pull out my 6 and square root of 2 pi to get 3 pi on the outside. I still have my integral e to the I omega t. I still have my 1 over omega. Remember, we're integrating with respect to omega, so we can't pull out the omega. So we have 1 over omega sine of 2 omega. Now the thing to consider is I have an e to the I omega t, and I have a sine of 2 omega. I can either convert this into exponential form, or I can convert exponential form to sine form. And I don't know, for whatever reason, I'm feeling like this is easier to convert because this is going to be using half angle formulas, and then I'm going to have too many terms, I guess. So I'm going to convert e to the I omega t to sines and cosines. I have then 3 over pi, integral from negative infinity to infinity. I have my 1 over omega sine 2 omega here, and my e to the I omega t becomes cosine omega t plus I sine omega t. And now at this point, it's a good time to stop and look at what we have because we are integrating symmetrically around t equals 0. So at this point, it's always good to stop and look at this. We're integrating symmetrically, and we have sines and cosines. So remember, the thing about sines and cosines is their cosine is even, sine over here is odd. This actually is an even function, and I'll show you why in a minute. But when you integrate an odd function symmetrically about the origin, your integral is going to equal to 0. So we definitely want to use that fact. As I had mentioned, cosine is an even function. Sine is an odd function. Sine over 2 omega divided by omega, that's also an even function, as you can see, because I graphed this using Wolfram alpha. I sort of cheated. But you can see this is also an even function. The thing is, an even function times an even function gives you an even function. An even function times an odd function will give you an odd function. Now when I multiply this sine 2w over w times cosine omega t plus I sine omega t, I have my sine 2 omega over omega times cosine omega, plus I went ahead and separated out this integral just to highlight the fact that we're going to be integrating an odd function, but plus 3 over pi, an integral from negative infinity to infinity, my sine of 2 omega over omega times sine of omega t. This here is an even function again, times an odd function. So this is an odd function integrated symmetrically around 0 is going to go to 0. So the only part of this integral that's left is this, well, how did I get 6 pi all of a sudden? I think this is 3 pi. Oh, I know how. Because this is an even function, this, when we integrate, we can just, and this was, you can, actually this could be your final answer, but what I did is I said instead of going from negative infinity to infinity, it's twice the integral, which is how I got the 6, going from 0 to infinity of sine 2 omega over omega cosine omega t. So this is our final answer here. This is our function f of t represented in terms of sines and cosines. Remember when I told you when we had our original f of t and then we converted to a function of frequency and then we convert back to a function in terms of time, but this function is going to be a different f of t. So this f of t represents our original f of t, but now we are representing f of t in terms of sines and cosines. And in that way, it's sort of like a Fourier series, which represented an arbitrary function in terms of sines and cosines. And that's exactly what we've done here for this non-periodic function f of t. I just want to mention, I didn't realize this when I was preparing this video because it's later on in your book. A different section of your book has Fourier transform examples, and it did a square wave. So it's very similar to this, but one, the height of the wave was 1, not 3. The period was left as, I guess, t over 2, and or t naught over 2. They didn't actually put in, they just had variables instead of the negative 2 to 2. And last, your book was doing an example of a Fourier transform, so its final solution was this here, the Fourier transform. They didn't go back and plug the Fourier transform into f of t. So those are the differences between my example and the one in your book. I have a second example for you. That's f of t equals e to the minus at squared, where a is greater than 0. And since your book doesn't seem to do the second step, we're just going to do the first step and find the Fourier transform of this function. Also, I didn't go over this, but for this problem, I'm going to say if you want to verify that you can do the Fourier transform. That's equivalent to saying that f of t converges as t approaches infinity. So when we look at this function, the limit as t approaches infinity of e to the minus at squared, that is 1 over e to the at squared. As t gets large, this denominator gets large, but 1 over something large approaches 0. So since it converges to something 0, we can integrate, and since we can integrate, we can use the Fourier transform. The second thing I want to say, because we're going to use this when we do our integration, this function here is a Gaussian form. The Gaussian form is given here. F of t is equal to alpha over square root of pi e to the minus alpha t squared. Here our alpha is equal to 1. Our Gaussian curve, this is what it looks like. I plotted this in Wolfram alpha. And this curve is often used in statistics, and you might recognize it as the bell curve, where the A's are over here, the failing grades are here, maybe the B's are here. Depending on what your school is like, maybe the C's are here, or maybe they're down here. But this is the curve that you see all the time when people give you grades, so you're probably very familiar with it. But the thing about the Gaussian curve is when you take the area underneath, or when you integrate under the curve, that your area is going to equal to 1, or 100%. Since we'll be using this formula here, I'm just going to stick it up here in blue so we can see it along with our little Gaussian curve. And now I'm going to plug in to my Fourier transform equation 1 over square root of 2 pi, integral from negative infinity dt, e to the I omega t, and then my f of t over here is e to the minus at squared. I can then combine my exponents, so I have e to the minus at squared plus I omega t. And remember, this I'm not sure how to integrate. I mean, I could integrate it, but what I have here is this formula for e to the minus at squared. So if I can make this look like a squared term, I would be good. I could use this formula right away. And so what I'm going to do is I'm going to complete the square so that I can get some squared terms. So here's my exponent, at squared plus I omega t, which I have copied here, and I want this to be in the form of p squared. I want this term to be my 2pq, and then I want a q squared term so that this can be p plus q squared, but then of course if I add my q squared, I need to subtract a q squared term. So this is the form I want it to be in. I'm going to say that p squared is equal to at squared, which means p is equal to square root of at. I'm going to say that this I omega t, that's going to be my 2pq term, which means that q is going to be my I omega t divided by 2p, which is I omega t divided by 2 times square root of at, because I have p solved for over here, which means that q is equal to, I cancel out my t's, I omega over 2 square root of 2, which means my q squared term then, my I squared gives me a negative, and then I have my omega over 4a. Which means finally over here, I can write this as p plus q squared. So p is my square root of at, my q is my I omega 2 over square root of a squared, minus my q squared. Since my q squared is negative, that's going to give me a plus, and then my q squared, omega squared over 4a. So I'm going to use that in my integral now. So I have e to the minus, and then I have my t square root of a plus I omega over 2a squared plus omega squared over 4a. Actually, I'm going to write that down here underneath so I can put a little arrow saying that I used completing the square. I'm going to get rid of my algebra over here, but I'll remind you that I got from here to here by completing the square on the exponent. And now I notice this term here, it doesn't have any factors of t, so this is a constant. So to pull it out, first of course I have to separate my exponents. So I have my exponent e to the minus t square root of a plus I omega over 2 square root of a squared, and then I have my e to the minus, I guess I need a minus over here, omega squared over 4a. And now I can pull this out as a constant. So I have my 1 over square root of 2 pi e to the minus omega squared over 4a, and I have my integral dt e to the minus t square root of a plus I omega over 2 square root of a squared. And now what I notice, this over here is starting to look like my general Gaussian, the negative infinity to infinity, e to the minus, and then something squared. So I can make it look like that if I do this substitution. I can substitute u is equal to this expression here, t to the square root of a plus I omega over t 2 square root of a. And then I have exactly this form. But to do that, I also need to figure out what dt is. So du here, this has no, it does not depend on t, so I'm just left with square root of a dt, which means dt is equal to 1 over square root of a du. So here I have my 1 over square root of 2 pi, my e to the minus omega squared, a to the minus over 4a, integral, negative infinity to infinity, my dt becomes 1 over square root of a du, and then I have e, and now this is just minus u squared. This portion, I could take out my 1 over a, and what I'm left with is negative infinity to infinity e to the minus u squared, which is this form here, exactly what's inside the integral where alpha is equal to 1. So this integral is going to be equal to 1 over square root of, 1 times square root of pi over alpha, and again alpha is 1, so it's just going to be equal to square root of pi. So my final answer is 1 square root of 2 over pi. I have my 1 over square root of a here, my square root of pi that came from this 1 and this alpha, which is 1 over square root of pi, is over here, e to the minus omega squared over 4a. And this is when a is greater than 0. This you will see is also in Gaussian form. So the Fourier transform of a Gaussian function is still a Gaussian. And also, I had done this problem before. I saw this in your book, but they also do transform of a Gaussian, but they have, instead of calling it a here, they called it a squared, and then they have a constant in front, alpha over square root of pi. To review what we have done in this video, we are starting our series on Fourier transform. The first thing we did was we reviewed Fourier series and the idea of this Fourier form of the function f of t is a linear combination of sines and cosines, because this e to the I omega nt represents sines and cosines. It's a weighted summation, and the weights are determined by these coefficients here, and the coefficients use the fact that sines and cosines are an orthogonal bases. So the c to the n, when we do the inner product, which is this integral, we pick out the nth bases, the omega n, the bases with the omega n frequency. The next thing we did is we defined the Fourier transforms, and we applied it to functions that were not periodic. We got these equations then are defined by looking at the Fourier series and letting t naught, the period, approach infinity. And what we have is this f of t. Now we can represent a function f of t with this formula here, which inside the formula has a Fourier transform, which takes a function whose variables are in t, so the domain is time, and it gives you a function whose variable is omega. In other words, the domain is frequency. So that's the significance of the Fourier transform. It'll take things from the time domain, map them to the frequency domain. But then we can plug this back into an f of t, and now we can get back our function, our original function, but now it'll be a function that in terms of sines and cosines. Also, I pointed out that these two formulas are remarkably similar. Really, the only thing that's different is the fact that our variable here is t, time, and over here our variable is omega. And then the other difference is this exponent is negative for our Fourier transform. It's positive over here. We did a couple of examples. We did one example of this complete kind of finding f of t using the Fourier transform and then plugging into the second formula. And then we did a second more involved function, and we only did finding the Fourier transform. So that's it for this video. Thank you for watching.